Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Preview of the episodes 25 to 28, The Theory of Everything. Episode 25. Rest in peace, Peter Higgs. So this April, Peter Higgs passed away, and he was awarded the Nobel Prize of Physics in 2013 for his works on the Higgs mechanism. It was, I think, the last Nobel Prize that was awarded to a physicist in this area, so in the area of theoretical particle physics. And his work has also been done. So the work that was awarded there had already been done in the 60s, but it took up to 2012 until CERN could really confirm the results he had made in his theoretical studies, or the theory he postulated, or the mechanism he postulated there. And I think in light of this recent event, I thought it would be a good way to remember it, and to also see what he is remembered for, what this Higgs mechanism that he postulated, what this is about, which problems it solves, why it is needed, and so on. So let's dive into this topic. And I know in the English podcast I have not talked that much about particle physics, so I have not done a deep dive into quantum mechanics and leading the way to particle physics and quantum field theory and all those topics. So maybe I need to, on some points, go deeper into some side points. But I hope really that you can follow along and understand the deeper topics I'm talking about, or understand what I'm talking about, the concept of what I'm talking about. So in particle physics, the aim is to really describe the foundational particles our universe, or the fundamental particles our universe is made of. And there is this standard model of particle physics, which basically describes all the particles we know of and how they interact with each other. And as I will also mention in different episodes, there are basically two bigger groups of particles. And those are, on the one side, the material particles, those like electrons, protons in a way, but protons are not fundamental particles. They consist of quarks, and those are the matter particles. And those two groups are basically the groups of matter particles. So leptons, which are like electrons and so on, and quarks. And there are the different kinds of quarks, different kinds also of electron-type particles. But you can just, if you are more interested into this, you can just Google standard model and you will find nice pictures of all the particles listed there. And what I also want to say to the leptons, so the electron-like particles, there's also a partner particle, which is the neutrino. So an electron has an electron neutrino, and the other families in that have also their partner neutrino particle. So this is basically the matter part of our universe. And then there are also, the universe is not just existing of matter, there are also force mediators. So the forces are mediated in particle physics. You describe this force mediation by the exchange of particles. For example, in the electromagnetic force, you would use the photon as an exchange particle for these forces. And in the strong nuclear force, we have the gluons, and in the weak nuclear force, there we have the so-called W and Z bosons. And as we will see later, those are the ones who will get a little bit tricky. But let's go back to the theory. And for this, you need to understand, so there is this area or this kind of making computations in physics where you make computations analytically by using so-called Lagrangian mechanics, or Lagrangian dynamics, where the idea behind this is basically that you have this Lagrange function, or Lagrangian, and with that you can, if you put it in the correct formula, you can get the equations of motions, which is basically what you want. So maybe I will do an episode one time on this topic because it's really fascinating, really interesting. I really liked it about the theoretical part of physics. But for now, it suffices to say that we have this Lagrangian. And what you basically do in particle physics is you add terms to this Lagrangian, and this Lagrangian basically describes your whole theory. So if you have a Lagrangian for the electron particles, that's just a term that you have in there. You have a term for the force interactions and all this. And maybe you, if you are into physics, maybe you have once seen these cups where there is this nicely drawn L and there's an equal sign, and then there are all bunch of symbols like a formula. This is basically the Lagrangian of quantum field theory. So basically it's our theory of everything, or our formula of everything, so to speak. And in this, all the terms are in it. And if you then would use these equation in which you can put it in, and you get the equation of motion, if you can solve this formula, and then basically you can describe the whole system. That's the idea behind it. And the problem there is, or what you then do is, every particle has a mass. And not every particle has a mass. That's wrong. There are particles that have a mass. The matter particles usually have a mass, and this term you add it just like a mass term. You call it a mass term, and this is actually for fermions. This is not a problem at all. So fermions are the matter particles of the universe. For them, this is not a problem at all. But for the force mediators, this would be a problem, because the fields or the theories describing the force mediators are in a way specific. They are, we call them gauge theories. And for this, we need to make a small dive into electromagnetics, because there this concept of gauge theories first arrives. And there we have the case that, for example, you have an electric field, and you realize, okay, if I just have some term that I can easily derive, and then I have this term, I call it phi, and I take the derivative, then I will get the electric field. This is in some sense makes it easier. Then what then happens if I only use this term to calculate because it's just easier? Then I know, okay, but if I just add some number, some constant number to this term, then it will, in the end, when I take the derivative, if you remember from your calculus class in school, then this will just vanish. So this term will just vanish. So basically, I can say, okay, I want this to look nice, so I add a constant that will always make this term look nice. And I know that I can do this because in the end, I take the derivative and this term vanishes. So as you see, I have a freedom in how I choose this term because it will vanish anyway. And the same concept, it might look silly to you, why would one do this? But if in the more complex cases like electromagnetics and gauge field theories, this is really important. And there you have this liberty, this gauge liberty, or gauge freedom to choose a gauge from which you in which you have your terms written down, and this makes many formulas a lot easier, and the calculations simpler, and you get it's easier to see the physics behind it. The problem behind this is, of course, or not a problem is, the problem is you cannot add, of course, every term to it, because if there are some terms, I mean, in as I described before, if I wouldn't have added a constant but a variable, then the derivative would have acted on the variable and there would be something left. So this I could not do because then there would be a change in there. And so I cannot just add any term to this gauge field or to this gauge quantity that I have there without having it removed in the end, or without, And therefore, I need to be, in these gauge theories that I have there in particle physics, I need to be careful which terms I add in order to keep this gauge invariance, as you call it. And the problem that now arrives is that if I have a mass term, such a mass term would not be gauge invariant. So it would not vanish, and it would not. It doesn't need to vanish. It would not be invariant under these gauge transformations that I have there. So it would just not work out then, and therefore it is not allowed for force-mediating particles, also for these gauge theories, for the theories describing the force mediations like electromagnetism, strong nuclear force, and so on, for them to have a mass term, to have mass. So, and this seems to at first not be a problem because for the electromagnetic force, this is not a problem because photons do not carry mass. They are massless. In a strong nuclear force, this is also not a problem because the gluons that are mediated in this force are also not carrying mass. However, when we come to the weak nuclear force, this gets different because the W and Z bosons are pretty massive. So those are some of the most massive particles that we know, much heavier than the electrons and all the other particles by far. But even if it would just be a small mass, just the case that the simple fact that it has a mass is already a problem. And because then we would need to add such a mass term, and we are not allowed to do that because then the theory doesn't work anymore. So this has been a real big issue. But before we dive deeper into that, I want just shortly mention why this is actually needed. So why do these W and Z bosons need to carry mass? Is there a necessity for it? And actually there is, because the weak nuclear force is actually not so weak. It would be actually stronger than the electromagnetic force. However, in effect it is not, because and this is exactly because the W and Z bosons carry mass. So each force has a coupling. It's basically the charge with which it couples to other particles. And how big this charge or this coupling is basically describes how strong the force is. And the coupling for the weak nuclear force is stronger than the coupling for the electromagnetic force. So it would be actually stronger, or it's higher. It's great. So it would be actually stronger. However, since for the force to be mediated, these bosons have to be produced. There's a much higher threshold for them to be produced because they are so heavy. For the electromagnetic force, this is pretty easy because the photons are massless. They can be easily produced, but for the weak nuclear force, they are really heavy, and so there is a lot. Takes a lot more, so to speak, for them to get produced and for this force to mediate with the other particles. And since this is responsible for the radioactive decay, it is also, or for beta decay especially, it's also important that they are not so, that this force is not so strong, because this would affect the stability of particles, because all the particles except for the proton and the electrons are not stable. So even neutrons would decay after 15 minutes if they are not in a bound state like an atom or something like that. And therefore it is really important that these W and Z bosons are so massive, because otherwise probably matter could not be as stable as it is. Anyway, now the question remains, how can we solve this? How can we keep our nice theory with gauge theories as force mediators and the matter theories? How can we keep this together and still have a working theory where the math works out and everything is working fine? And the solution for this was found by Higgs, by his so-called Higgs mechanism. And what he did is he postulated a Higgs field, basically, or a field a scalar field. So this is in contrast to the fields we have discussed before. So a gauge field would be a spin 1 field, you would call it. Matter fields are fermion fields are spin and half fields. You don't need to really understand it. It has to do with the property of quantum mechanics called spin, but it basically says they have some kind of direction in which they kind of rotate. But the Higgs would not have this. It's just a scalar. We simply just like a value. And this is the only particle with that property that we know of. And it has then, so what this particle or this field then has is a so-called WEF. That's a vacuum expectation value. And this is basically the potential of this field. And this basically, it looks like, it's also often called the Mexican head potential. So it looks kind of like a Mexican head. Or if you know from the wine bottles, the bottom of a wine bottle where basically there is this, also this Mexican head kind of shape. And what this basically does is that the Higgs field has a non-vanishing expectation value. So the expectation value is basically the value that you would expect, that you are to expect in any given system. So since physics, or especially particle physics, is highly probabilistic and statistical, you cannot say give for everything an exact value, because that would be against Heisenberg's uncertainty principle, and therefore there are fluctuations anywhere, but there is always an expectation value, so an value that you might expect to occur there. For example, in vacuum, for most fields, this expectation value would be 0. You would not, in a vacuum, you would not expect electrons to occur there, for example. But for the Higgs field, this is different. It has a non-vanishing expectation value, and therefore the Higgs field is basically present everywhere, even in the vacuum. And this breaks this kind of symmetry. What this now means is that particles that are interacting with the Higgs field, like for example these W and Z bosons, they are getting more inertia by interacting with the Higgs field. You can imagine this like, so imagine you have a spoon, and you in the beginning you move it just through the air. You have your spoon and you move it through the air. It's simple, right? You don't need much force. It's not really inert and so on. But then you take the spoon and you move it in a bucket of honey. And you try to move it around in the honey, and you will realize it will be a lot harder to move the spoon around than when you were just moving it through the air, because the honey is really thick. It's really resisting the movement of the spoon, and the spoon is getting a lot more inert. And the same actually happens for these particles in a Higgs field. So if there would be no Higgs field presence, the particles would just speed at a speed of light without anything. But by interacting with this Higgs field, it's for them like going through such a pot of honey, and then they are really slowed down. They behave like they would if they would have a mass, because by interacting with the Higgs field, they kind of obtain a mass. And this is how these particles obtain a mass, and therefore you have this property. But for example, photons do not interact with the Higgs field, and therefore they are still behaving like they are massless, because they are. And with this mechanism, you can successfully save this symmetry, basically, or save this gauge theory, or this gauge invariance. So you don't have to add a mass term which would screw up the gauge invariance. And more than that, you can even get rid of these mass terms altogether and let the fermions get a mass through this through the interaction with the Higgs field too. So I think this is really a beautiful concept, and I think you can really also interpret this also in the spiritual, because what the Higgs field really does is it gives particles their mass, and therefore it gives them their weight, you can say. And in today's age, oftentimes that you have a negative image of weight or of mass, but I think you can also look at it in the sense of influence, in a sense of majesty to some degree, and also in the Bible, oftentimes the word that there's used for glory is often the word they used is often the weight or the heaviness of God. And I think therefore you can see this. So there's also another interpretation of the Higgs field or another visualization of the Higgs field, where you say if you have an influential person like a politician or some high ranking official or something who is in a room, and then there are a lot of people who are crowding around him. And then it's more difficult to get him through the room, because there is this Higgs field basically that crowds a lot of people around it, and to get through it you would have more inertia, because it's more difficult to get through. And there you also have this visualization of it being a heaviness, or even there you have directly this image of a influential part of this heaviness, or this comparison between that. And I think you can see this also in the spiritual, that this is that shows that people who interact with or particles who interact with this Higgs field, the stronger they interact, the more weight they gain, the more influence, so to speak, they obtain, and the more they get basically massive in a way of a heaviness, of an influential way. And I think in the spiritual it's exactly the same. The more we interact with God, the more we interact with His glory, the more we get this heaviness, we get influential in a positive way, of course, in a way that is also God wants us to be influential in. And therefore this is a powerful statement, a powerful image on His glory and what it does when we really continuously live in His glory and really also interact with it, not just be like photons who don't interact with the Higgs field at all, but really interact with it. And also this Higgs field has as we have seen, a vacuum expectation value that is not vanishing. This means the Higgs field is everywhere, and I think this is also shows that God really is everywhere. That He's not even in the remotest places. He is not. He's not missing. He's still there. There's still a remnant of Him remaining there. He's always accessible. He's everywhere. He's omnipresent. But still, also, of course, the more we interact with Him, the more we also, like at CERN, where they try to produce this Higgs particle, the more energy we put into it, or the more we yield to Him, the more He will be present, or the more he will be able to show Himself up to us. And I think that should also be our goal, to really get ever closer to Him and to really experience Him ever more. What also I think is interesting, this case of the electromagnetic force being stronger than the weak nuclear force, although the weak nuclear force actually has the higher coupling. This is similar to the case that gravitation is the force you immediately experience, the force you first know about, also the force that was first physically described. But it is actually, if you look in the list of all the forces, it's the weakest of them all. And I think from this you can see that what has the greatest influence is not always really the strongest. Or on the other hand, what on the fundamental side looks like the strongest must not always have the greatest influence, and so on. And I think this you can see also reflected in the Bible, that God uses God uses the weak to do greater things than he could have done through the strong. Or you see this repeatedly in stories of the Bible, just as you have seen in examples of David and Goliath and so on. So this is what you see there repeatedly, and it also shows you that, as it says with David in Samuel, it says that God looks in the heart and not what is in front of his eyes. This relates to the story where Samuel was anointing David to the king, and at first he thought it's one of his brothers who looked really strong and powerful, but God was looking at the heart, and he liked the heart of David, and so he got anointed king, although in the natural he wasn't even considered by his dad to be worthy to be brought to Samuel. So I think this is also what this shows, that what in the world might look as the strongest is not necessarily the strongest on a fundamental level, on the heart of the issue, so to speak. And God looks at the heart of the issue. God looks at our hearts. God looks into our hearts. So this, I think, is also a pretty powerful interpretation of these facts. Now back to the Higgs mechanism. So by now it really is basically confirmed that this mechanism seems to occur in nature. It was formulated in 1964 by Peter Higgs, and in this Higgs mechanism, this Higgs particle was predicted. So basically we always were talking only about a Higgs field and so on. You need to realize in quantum field theory it's such that everything is basically a field, and particles are just the excitations of those fields. It might sound a little bit confusing. It has to do with quantum mechanics being a bit confusing, but also it's basically just the way it is. So in quantum field theory, you describe basically all the quantities as being fields, and the particles are then the excitations of these fields. So the Higgs field, as I have said, is non-vanishing. So it's basically everywhere, but the excitation of the Higgs field, which would yield a Higgs particle, this was achieved by CERN at their Large Hadron Collider. And on 4th July in 2012, they could finally confirm that this Higgs mechanism seems to be occurring in nature. So is the work done with that? No, there are still issues. For example, in the theory of the Standard Model, neutrinos are still considered massless, but as we know from neutrino oscillations, they do carry mass. So this is one of the unsolved issues. Also, we have a so-called hierarchy problem. This is a little bit more complex. So in quantum field theory, it is the case that you have infinities occurring in your calculations, basically, if you do them, and this is a problem, and there you needed to invent or postulate develop a mechanism which basically gets rid of these infinities. This is called renormalization, and what you do in this renormalization is basically these infinities, you push them into some constants like the mass, for example. Then you have basically a bare mass of the particles, and then you have an effective mass, and in this effective mass, this is basically the bare mass plus these infinities. You can really also understand this physically, how this comes about, why these infinities occur, and why this is reasonable to behave in this way. But it also means that this theory is not a fundamental theory, but an effective theory, because by doing that, you lose the predictive power, some of the predictive power that this theory had, because the constants are now not anymore predicted by theory, but they are set by the case that you need to use them to get rid of these infinities. And the problem there is in these corrections, with the Higgs particle, it is such that these corrections would yield really high masses for every particle, which we just do not observe. And the only way to solve this would be that these masses cancel each other out perfectly. So these corrections depend on occur through particles like the Higgs and other top quarks that occur in these corrections. So it's complicated. If you don't get any of it, don't worry. But basically, it says that the particle contributions of each corrections, they cancel each other out, just that it fits, and this is a lot fine-tuning, and therefore the physicists do not really like the fact of that it's not really aesthetic, and therefore other theories who are able to solve this hierarchy problem or the physicists are looking for other theories that can describe this, and one of this theory is the supersymmetry. And this theory basically says that for every particle that we know of, like the electrons, the protons, not the protons, the quarks, and so on, for each of them there is a super partner. So that's the symmetry, that each particle has a partner which has similar properties, but is different in kind, that it is. So for the matter particles, I told you that they are fermions, and for the force particles, they are bosons, and this has to do with their spin. The spin of bosons is integer, has a full integer, and the spin of fermions has a half integer size. And this is this basically, and the symmetry there is that the partner of the fermions would be a boson and the partner of the boson would be a fermion. This is in supersymmetry the case, and by doing that you can basically have these corrections such that each partner cancels the contribution of the other, and such the correction remain as small as they need to in order to do not lead to higher and higher masses. So this is one problem that supersymmetry would solve. However, all these partner particles of supersymmetry could not yet be experimentally confirmed. However, many predictions said that they should be confirmed somewhere around now. I mean, it's always playing around with parameters, so you can always adjust such that they are at still higher masses where they have not been observed yet, but slowly the time seems to be running out for this theory. But it was for a long time a really promising theory to especially solve this issue and also find solutions for issues like dark matter, because of course you could just say of one of these super partners could be a candidate for dark matter. Episode 26, Intellectual Awakening. So when talking about science and faith, it is oftentimes it looks like they are two completely distinguished things, two things who are not really completely distinguished, but also do not really work well together. So many people think there's a contradiction between science and faith, and that you can either believe in the one or the other, and that to believe in science would automatically rule out any belief in Christianity or in a God or in something like that. And this is kind of what you oftentimes, what many people assume to be true. And part of this podcast, or one goal of this podcast, is of course also to show that this is not the truth, that this is not actually true, and that it is indeed possible to believe all the statements of science that are based on facts and still be able to believe the statements that the Bible make, that there is no contradiction, and that those contradictions can be easily resolved if one dives deeper into it. And this is, as I said, one goal of this podcast, and I think it's also important to learn this, because it's also important to learn that there actually science cannot disprove God, and that it's just not by construction not possible for science to do that. But still, in this podcast, you should know this. You should have, from the content that I produce, you should have gotten the idea behind this. You should know this. But if you look into secular culture or in mainstream culture, you won't get this feeling or this this sense that this is the case, more or less you will get what I described in the former. And this was not also always the case, I think, if you looked deeper into history. But is for some time now it has been the case, so that this conviction that atheism seems to be the concept that is best described or best in line with science. On one hand, this is by construction in such a case that one says, okay, one has this materialistic atheism or this scientific atheism, which basically says that since in science we only look at the material, material things and do not care about what happens in the world beyond that, if there is such a world, since we do this, then we are basically in science effectively acting as atheists, if we are ones or not. And in some episodes I already talked about why I also see this in some degree as the problematic. I mean, as an effective stance to say, okay, I will not bring my allow my convictions to blur the scientific endeavors I do. That, of course, I agree with, but you can also push this to an extreme where it's also where you, instead of pushing your faith in the scientific, in your scientific work, you push it so far out that it amounts to the same problem. But this is a topic for another time. What I want to talk about is how this comes about, that basically if you look in mainstream culture, basically it looks like this thing that is the statement that science and faith are not compatible, that this seems to be considered true there, although it isn't. And this has been, so the atheistic movement has been around for some time, or that there are atheists among scientists has been around for some time, but it was not, I would say it wasn't so in the beginning. I mean, in the beginning of modern science, there, of course, not everyone was a Christian then, but there were many Christians. So many of the founders of the scientific method, especially like Johannes Kepler or Isaac Newton, Blaise Pascal, and so on, they were devout Christians. Other people were more on the agnostic side. And as I also argue in my book, I believe that they, being Christians or deeply rooted in faith, or at least in some cases, maybe not deeply rooted in faith, but still growing up in a Christian culture, I think this had a huge impact on the scientific method coming to what it is, and on the scientific revolution, as we call it today, to get rolling. So I think this was a huge impact, as I also describe it in my book. But there were also, at this time, you have to just accept the fact that there were already people who were maybe who were about agnostic, who were not really sure whether God existed, and then also there were other convictions. Also Einstein, for example, I think he was a person who believed in a God, but he believed that this God was not a personal one, so he did not believe in a personal deity. And there are also all along this spectra of scientists believing in God, or where there are also after later times there were many scientists still who were devout Christians. So, for example, James Clerk Maxwell, who made huge contributions to the formulation of electrodynamics, or Michael Faraday, and many others. But there were also many, or most, I would say at this time, most scientists were kind of, in some sense, agnostic. But with later times, there were more and more also scientists who were increasingly becoming atheistic. And I think one of the first, especially in physics, one of the first well-known physicists who really was a staunch atheist, so to speak, was Paul Dirac. And he was such an atheist that people said about him this statement that there is no God and Paul Dirac is his prophet. So this shows how much of an atheist he was. And while this statement also implies that he was pretty, so to speak, evangelical in his atheism, at these times you do not really get this sense that these scientists, being atheistic in their convictions, had a problem with faith as is, or were going against faith in thinking it's harming or harmful or something. They were just unbelievers, so to speak. And around the 2000s, there was a movement coming up that was called the New Atheists, or many call it the New Atheists. And those were people like Richard Dawkins, Christopher Hitchens, Sam Harris, and some more. And they were not only making the case that Christianity or faith is not true. They were not only of this conviction, but they really were convinced that it is harmful, that it is bad for people. I'm not sure if you can count Steven Weinberg into that group, but he, for example, he's a well-renowned, or was a well-renowned physicist who who also won the Nobel Prize for his work on the Standard Model. And he made the statement that where he basically was of the opinion that religion just makes bad people worse and good people bad, or something like that. And but the New Atheists basically had similar convictions, and also thought the God that is presented, for example, in the Bible, is a God that they do not deem worthy of worship, or do not deem as a good God. And so they really made this point that faith is not just untrue, but also in a sense harmful. This can also be seen by the book Richard Dawkins wrote, where he which he called the God delusional. So he said it is something like a delusion, something delusional, and basically made this also the statement that a world without religion would apparently be a better one. So, however, just recently, especially this Dawkins recently in an interview, he talked about Christianity, and he says he considers himself to be a cultural Christian. And by this he means that he does not believe Christianity to be true. He does not believe the stories of Christianity to be true. He does not believe that Jesus is the Son of God, and that he died and rose again, and so on. This he does not believe, but he likes, or he thinks that the Christian traditions have some value. So he was speaking about Christmas caroling and such traditions, which he found, which he said that he liked and that he found valuable, and wanted to keep in our culture, since he, I think, realized that some of this is decreasing in our culture. So I think an interesting response to this was from somebody on Twitter who said, yeah, but what does happen if you cut the roots from a tree? How long will it be able to survive? And I think that's the case that comes with this sense of, just culturally Christian. If you cut the roots of a tree, it will not survive long. And in the same matter, if you cut Christianity of its foundational principles, of its foundational truths, because you don't consider them to be truths, then the rest will also cease to exist very soon. And I think this change of mind, as it seems to be in Dawkins, also comes about because of a revelation, or not a revelation, or something that that was some revelation by experience basically in the last years that this secular humanism that they kind of were advocating for, that this seems to not achieve the same results, because Dawkins was also involved in a debate or a discussion about when he was in New Zealand, and there they have now a law where they basically state that next to science, which they consider Western, also concepts of tribe religions that have their way of doing a kind of science or whatever it is for finding truth needs to also be taught in schools on the same level as science. And he was not agreeing with that, because he said science is objective. It's not a Western thing. It's an objective way of finding truth, and it's also in this way superior to other ways of finding truth, like what some other tribal traditions also have come up with. And this received some backlash, but still he stood firm there, and maybe there was this realization that this secular humanism cannot protect something like science from these from other things, and therefore these traditions or the science itself, since as I also argue that science itself comes about from the Christian tradition, this also is protected by these traditions, and without it, it will also cease to exist. And if you look at it deeper, you will even also see that atheism in itself is in some sense based on Christian worldviews, Christian morals, because if you can argue that the God that the God you're considering is not a good one, then you need to have some concept of what a good God would be, and this you also get from faith. This does not fall from heaven, and therefore, if you look closer into it, atheism itself is founded on Christian ideals, and also you can see this by this kind of, especially with the new atheists, this evangelical way of trying to spread atheism, you might even say, so this evangelistic way in which atheism was propagated there, which also comes from Christian convictions, of course. Also, the importance of truth of what is truth, what is true. This also comes from a Christian worldview if you look close into it. And somebody who really also writes about this and many things more is the historian Tom Holland, who I also have mentioned on this podcast. And he wrote a book, Dominion, in which he describes the effect Christianity had on our Western worldview and our Western thinking, and on the values we hold dear, and also on many values you might not traditionally or many convictions or movements you might not traditionally consider to be Christian or based on Christianity, how they still in some sense have Christian roots, or even movements that like for example atheism, as I stated before, that go against Christianity or that seem to contradict Christianity, how they are still in some sense, or some ideas that they use are still rooted in Christianity itself. And Tom Holland himself, through this book, he came to this realization, or he wrote this when he had this realization, and then he did this research and wrote about all these topics. It's really interesting, really fascinating. So I encourage you to read this book. And also, if you are interested, he has a podcast, Rest is History, which is also very popular, where they talk about all kinds of historical topics, and he's always fascinated by this topic of how Christianity shaped our world and our thinking. And what he also had recently is so this kind of, I would say, I would interpret his thinking that this kind of made him to an agnostic, to somebody who acknowledges that there is an effect this has had, and that there might be, that it might show to that there is more to faith than it looks like. And he also had then this experience where he had a cancer in his body, or he was diagnosed with a cancer in his body, and they said they needed to remove some part of his inner organs, and to remove this cancer also. And in his desperation, he went to a church and made a desperate prayer to God. And when he went back and to the doctor and let himself be diagnosed again, they said, no, we don't see anything, we don't need to do an surgery or something. And so this was kind of a miracle that he experienced, and which of course made him maybe much more of an agnostic, and where he really can appreciate that there might be more than just our material world. And there you see that among the intellectuals there seems to be a shift, that there seems to be a shift from where before, especially with this new atheist movement, it was kind of like, to be a intellectual, to be a scientist, to be someone in academia, you have to be an atheist, where this was before the worldview. It seems to, in some places at least now, be shifting more and more to at least to agnostic worldviews, at least to something where you say, okay, there are values that the Christian faith has brought forth that we cannot reproduce with any secular humanism or any other concept, and there are things that we are convinced of by our deepest convictions that are, if we look closer into it, deeply Christian. And therefore we need to reevaluate some things we might have thought before. Now there is also many of these people are then of the conviction, okay, this Christian stuff, so to speak, is maybe metaphorical true, or it's helpful. Those are maybe things that evolved with society. Those stories evolved and they were very helpful for people, and they are still very helpful. And therefore, although the stories are not true and it's all just myths and so on, they are good in a sense that they are helpful, and therefore this is how we should proceed to look. Basically, as Dawkins said, to consider us cultural Christians by keeping the traditions, but getting rid of the foundations. But as this makes completely obvious in the picture of the tree without its roots, this cannot work out. A tree, you cannot just say, okay, I will just keep the tree, but the roots I will get rid of, and then the tree will blossom as it had before. No, this will not just happen. The tree will just die off. And this image is really, I think, really fascinating, because as you can see here, it is also the roots of a tree. They are on the ground. You cannot see them. Usually you cannot see the roots of a tree because they are underground. And you can only see the tree itself and see the fruit it brings forth, see the positive things it brings forth, but you cannot see the roots. And even if you would see the roots, if you are not don't know anything about biology, you would think, what is this stuff? This is just messing with the ground. This is just useless stuff. But actually, the roots are really important. Without the roots, the tree will die off. And in the same sense, it's I think with faith that the roots are the things you cannot see, that are beyond our understanding, our scientific, beyond that what is what we can reach scientifically, what we can describe that scientifically, which are in the area of faith, which are in this supernatural area. And without this, everything else cannot exist for long at least, and these the Christian culture and the moral values, the traditions, and so these things where we can come to the conclusion that they really are of value, are not will not exist for long if the roots are not, if we do not also invest in the roots. If we cut off the roots, they cannot exist. So in this sense, if we do not consider Christianity to be true, then but we think the culture and the traditions it brought are nice and are good and are to be conserved, then this will just not work out, because as impossible as it is to conserve a tree without its roots, as impossible it would be to conserve Christian morals and traditions without the roots on which it is founded. And this is the fact that Jesus died on the cross and rose again, and that the Gospels are the truth, and that the biblical stories are the truth that God tells us about this world. And therefore, I think where many intellectuals still make this mistake to think, okay, you can just separate it and say, okay, we conserve the things we do like, and the things we do not so like, we just push away. This, I think, will not work out, and either Christianity is completely true, and then we have to accept all of it, or it is not, and then we also have to reject all of it. And this is also what, for example, Paul said, where he says that if Christ is not resurrected, then all our faith is in vain. So what this now means, I think, or what this these intellectuals who starting to come to the conviction that there might be more to faith or not, what this will mean, if this really will lead to an intellectual awakening, as I stated in the title, or if this will just lead to them becoming more agnostic, or if this will fade, whatever. I think what it means at least is that faith and science are not contradicting each other, and that it is indeed possible to be an intellectual, or to believe in science, to believe the scientific facts and so on, but still also believe God, believe that Christianity is true, that Jesus rose from the dead, that there is no contradiction. This is shown by these. This is the least what this shows. So before we continue, let's have a short break. And I thought in these breaks I will shortly give you just some insight into my new novel, Alien Thoughts. So if you not have read it yet and you are still trying to think about, do you want to get it, do you want to read it, is it something for you, then I think with these short extracts you will get just some idea whether this book is something for you. So let's start. The Planetary Protection Headquarters was already bustling with activity. Patricia walked quickly to her office. Even though most of her work was done by artificial intelligence machines, there were still enough tasks that required the skills of a human. In addition to maintaining the machines, developing new and better algorithms for the AIs, and finding solutions to processes the huge and ever-growing flood of data, a lot of monitoring activities had to be conducted. The AIs were good at maintaining control without human help, but every now and then problems arose that they were not equipped to handle. That was the job of people like Patricia who worked in this area. Every day she sifted through the logs of what was happening and what the AIs had no answer for. In the best case, a generic solution was found, which was then implemented in the AIs, further improving them. Patricia focused mainly on monitoring the American territories, also known as rebel territories. When Gerald King tried to prevent the NCD 2000 from going to the market, failed and was fired from his company, he founded a movement to politically oppose the introduction of the chip. He set up an office in New York City and tried to achieve independence from the chip technology. This went under the name Negotiations of Independence, or NOI for short. His efforts were in vain, but he found enough supporters who formed a community in Arkansas and resisted the coercion of implanting the NCD 2000. When government pressure became too much, they went into hiding. Since then, nothing has been heard from Gerald King and his followers. But in the years that follows, there were rebel groups in the American provinces. It is suspected that Gerald King led them from the underground. The rebels were familiar with the chip's technology and knew how to minimize its influence. Over time, the rebel movement grew. Eventually, it succeeded in overthrowing the administration of the American province and established a rebel government in its place. Spurred on by this success, they declared war on the New World government under Boris I. A big mistake, as it was soon to prove. In the course of the conflict, many former major cities, such as New York and San Francisco, were completely destroyed. People fled to the countryside began a primitive life as farmers. Many believe that Gerald King died in this war, as he is believed to have been in New York City during its destruction. Boris offered all who submitted to the terms of the planetary government a life of prosperity and left the American provinces to the defeated rebels. These continue to live in pre-industrial conditions to this day, and nothing seemed to change this fact. That's just a short extract. It's about at the beginning of the book when the plot starts to move and it starts to begin. And if you want to find out more, if you are interested in how it will continue, what will happen, what this is really all about, then I really encourage you to get it and to read it. So you can just go to Amazon, type in Alien Thoughts and my name, and then you should surely find it. And if you have already read it, then I really hope that you give a review and this way help other readers to get aware of this product and to know if this would be something for them, and encourage them to get it as well. So thank you for your support. Episode 27, String Theory. So now is finally the time where we will talk about string theory. So I think in the English podcast this is nothing so special because I did not tease it as much on the German as on the German podcast and did not follow through until now. But still, I think it's a big deal to now be talking about string theory. I think on the English podcast there was not as much background as you might have noticed in the episode about the Higgs mechanism, that there was a lot of background I needed to cover still. I hope this will not be as much the case in this episode, because I also am basing it on an introduction of somebody who also did this for people who are have not that much background in particle physics and so on. But if it's needed, I really will dive deeper into the background for you to really understand what this theory is all about. So let's begin. At first, we need to answer, okay, what actually is string theory? What do we mean by that? What does it say? And if you just ask people around or type in Google what is string theory, you will hear different things, and one of these things might be it's a theory about quantum gravity. So quantum gravity is something that is often used to describe what string theory is, or also more generally a theory of everything. So a theory of all the things, of everything, whatever, or word, yeah. So let's go with the latter. So theory of everything. So what is everything? What do we mean by that? Okay, everything is this whole universe. So basically planets, stars, water, people, animals, trees. Okay, so then let's just start with one. People. What are people or humans made of? Humans are made to the most part of water. So, okay, what is water made of? Water is made of 2 hydrogen and 1 oxygen atom. Okay, atoms. What are atoms made of? Atoms are made of a nucleus and an atomic shell. And this nucleus consists of protons and neutrons. And then those protons consist of quarks. So quarks, what are those? Those are particles. Those are point-like particles, you say. So they are in our current theories, they are the fundamental building blocks of matter. Okay, matter particles, foundational or fundamental building blocks of matter. So that's where we are. But this is not everything. We have these matter particles. They are also not only the quarks, as we saw in the episode about the Higgs mechanism. Also, there are not only the quarks, but also electrons and electron-like particles. So before, when we were talking about atoms, we were immediately going to the nucleus. But I also mentioned there's also an atomic shell, and in this shell there are electrons. So those are also matter particles. But those are not all the particles. There are also forces. So, for example, electromagnetism is a force, or the strong nuclear force which holds together the nuclei, or the weak nuclear force which is responsible for radioactive beta decay, for example. And those as we also heard in the episode about the Higgs mechanism, those are produced by exchange particles, and those particles are, for example, photons for electromagnetism, or gluons for the strong nuclear force. And with all this, if you all put this together, and of course also with the Higgs that we heard about 2 episodes ago, then what we achieve is the so-called standard model, where we have all these particles in there that all together describe almost everything that we experience around us. I said almost everything because if you thought along which force I might have missed, then you would have understand, okay, something is missing, and that's gravity. Gravity is not part of the standard model and is not described by it. And this is kind of odd because it's something we experience every day. It's the first thing or maybe the first forces that we experience in our life where we really understand it as a force. So why is it that this is not at all included in this standard model of particle physics, in the standard model of the universe that we currently have? And the reason for that is that gravity is different than all the other forces. Because for once, it results from the curvature of space, which is different than the other forces being mediated by some kind of particles, or even if you look at them not on a particle level but on the classical limits, it's still very different that gravity results from the curvature of space, from a property of space itself, and that this is responsible for gravity to occur. And another thing that is really different about gravity is that it works on everything, that it influences everything. So everything is affected by gravity. So if you just know Newtonian gravity, you might say, no, that's not true, because it only works on matter, on things that really has mass, that has a weight, that has mass. But if you look into general relativity, which is the description of the current description of gravity that we have, you will see that this is not true, that it does even work even affect light. So even light is affected by this curvature of space and therefore by gravity. So nothing can get away of gravity. Everything is gravitational interacting, and this is not the case for the other forces. For the other forces, they all have a charge. So they have the particles participating in this force have a charge, and by this force is mediated. For example, in electromagnetism, you have the electrical charge, and particles or objects that do carry electrical charge take part in this electromagnetic interactions. The same is, of course, true for the strong nuclear force and also the weak nuclear force. However, for gravity, this is not the case. For gravity, everything is affected. And this leads to a problem, because then gravity, or a graviton, if you would postulate it, would gravitatively interact with itself, and this in such a way that the closer you look into it, the more you see things that a graviton will interact with, and therefore at the place where the graviton is, there would be so much energy, so much interaction, that it basically would become a black hole, as we learned in one of the last episodes, where we talked about the problem that quantum gravity has, or that the problem that one has when one tries to come to a theory of quantum gravity. So the question is, how can we resolve that? How can we resolve that? Do we get away of this contradiction? And the idea is that what we see as a particle is not actually a point-like object as in our particle theories, but actually it is something like, or not, it is a closed string. So it is like a string, and this is closed, and this is the basic idea of string theory. So we basically avoid this by saying you cannot go ever closer to this graviton, and therefore always more and more increase the energy, because at some point it won't be you won't get closer, it will just be this closed string, and not a point-like object where you can get closer and closer and closer to it ad infinitum. So this is the basic idea of string theory, and hence also, of course, the name string theory, because it's a theory that postulates that the fundamental building blocks of matter are strings. So now if you know from music theory, basically, that if you, for example, have seen a guitar, that if you have a string and it can swing, it can have it can oscillate and so on. And it can oscillate in different modes. And in string theory, you say that all these different modes in which this closed string can oscillate, all these are different kinds of particles. So, for example, if it vibrates in this one mode, then it would be a quark. If it vibrates in this other mode, then it would be a photon. And in again another mode, then you would have this graviton, and so on. So this is really satisfying, because instead of a kind of a zoo of particles, as you have in a standard model, where you have families of particles and so on, and many particles, in this case you really just have one closed string which is vibrating in different ways, and this all leads to the different particles we see. So with this one closed string, you can basically reproduce all the many different particles that we see in the standard model. So you have really simplified this whole standard model just to one closed string. So, however, it's not that perfect, because you also get some problems. And the greatest problem I think you get into is that this theory is mathematically only valid or only workable if you have 10 dimensions, if you are working in 10 dimensions. However, if you look in the world around us, you will quickly realize that we only have 3 spatial dimensions and 1 dimension of time. So we only have 4 dimensions. So 6 dimensions, where are they? Where are the other 6 dimensions? And instead of dropping this theory, then what one does is one says, okay, the other dimensions, they are just rolled up. And to understand this, you have to think of, for example, if you think of a two-dimensional plane, and you like a sheet of paper or something, and if you have like an ant or some small animal walking around it, it can of course go into these two dimensions. It can go horizontally or vertically along this plane, along this sheet of paper. However, if you now start to say, okay, I will roll this sheet of paper up really, really tight, really closely, then for the ant, if it's close enough, at some point, the ant will only be able to walk in one direction of it, because it's in the other, it's so rolled up so tightly that it basically cannot walk into that direction anymore. And for the ant, it will in the end be basically a one-dimensional object. Another way to illustrate this would be to think of if you have a metal, a plane of metal, and you roll this up like a pipe, for example, and you do a really narrow pipe, and then you walk over it, like you try to walk over it, and then for you it will also be one-dimensional. You will only walk in one direction, because in the other it's just too thin to really be something where you could walk along, and therefore it would be, although it is a two-dimensional object in the beginning, it would occur to you like a one-dimensional object. And in string theory, you basically make the same assumption that all these 6 dimensions, they are rolled up such that they are not visible to us, that we cannot see them, that we cannot experience them, although they are there. And this is pretty complicated mathematics, with which you can achieve that. And in the end, you will have a result, or it will result in a world as we see it, and you have this problem of the graviton resolved. However, with all this, the question is it true? Is nature really in that way? Are there 10 spatial dimensions, and the ones we do not see are just rolled up? Or is there a different theory describing all this? And the thing to know if it's really true, of course, we have to make an experiment and see if it is true. The problem with that is that those strings are really, 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 really small. So they are at the Planck length, and the Planck length is about 10 to the minus 35 meters. And it's to show you how small this is, if you would take one atom and increase it in size so far that this one atom would be as big as our universe, then this string that we are talking about would be about 1 meter. So it's really small. Even on the scale of for an atom, it would be just even small. So it's basically impossible to resolve this to really find to confirm directly the existence of strings, and therefore we need to confirm it indirectly. So, and this so far has not worked, or is not really promising, because the prediction that these indirect prediction that string theory would make are really hard to prove, or there are not many of them, and those that there are really hard to prove. They require really high energy experiments, which so far we do not have in some cases. So it's really hard to prove whether this is actually the case. And also, I think as beautiful as the simplification of describing all the particles by one string which is vibrating in different modes, as beautiful that is, as ugly to some degree is this complication with all these additional spatial dimensions and so on. Therefore, I'm still not really convinced that this theory is showing the truth. Also, it really is the ugly part of the theory really is also that it is kind of hard or impossible to prove, not only because of the difficulty in resolving such strings or the impossibility of resolving such strings, but also because there are really few predictions this theory makes. And the theory, as many say, is always only just as good as the prediction that it makes. And if a theory does not make many predictions that really can actually be confirmed in doable experiments, then this theory is all really of less value than a theory that does. So therefore I'm still very skeptical about string theory. Also it has some charm to it, of course, and what I think is especially fascinating on this is it shows the fact that gravity is really affecting everything, is working everywhere, and I think this is can also be considered as an image on God, that he's really affecting everything, that he's working on everything, and that he really pulls us to him, or wants to pull us to him, and if we yield to him, he will do that, and he will pull us to him, and he will really change everything about us, because just as gravity affects just everything, God will affect everything of us and also change everything of us if we yield to him, if we give ourselves to him. And I think this is powerful, that you can see in this problem this gravity has. You can see how powerful on the other side this is in its spiritual implication, that if you consider God to be like something, God's power to be something like gravity, that it affects everything, and that the closer you get, the more powerful it will be, the more it will reach to infinity if you look at it on a fundamental level. So scientifically it might be not really sensical or not really makes sense what I'm saying there, but I think in the spiritual that's a sign that, or you can interpret it in this way, that it really shows how powerful our God is, and that everything in us can be changed by him, and that nothing is out of reach for him, and that he's really able to transform us. Episode 28, Gravitational Waves. So if we look at electromagnetism, we see, so electromagnetism is probably one of the forces we first realized to be existent in this world after gravity, to which we will come in a bit. But if we look in the world and we see the electromagnetism going on, for example, when we see lightnings during a thunderstorm, or all these effects that you can experience where electromagnetism is behind it, then people started to, so after they described gravity by Newtonian gravity, they started to describe electromagnetism in physics. So, and once by once they came to a theory that we know today as the theory of electromagnetism. And at first it was not completely clear that magnetism and electricity was really connected. There was always a hint of it, and pretty soon it became clear that there has to be some connections, because through an electric field can stimulate or changes in the electric field, timely changes in an electrical field will always induce a magnetic field, and the other way around, changes in the magnetic field will also induce an electrical field. And this was shown experimentally, and then equations were developed which described this in a theoretical way. And one guy who was able to put all these equations describing electricity and magnetism, one guy who put these equations all together was James Clerk Maxwell, and therefore these equations are called the Maxwell equations, and they describe basically all electromagnetic effects. So what if you have this theory and then you have these Maxwell equations? What you can do then is, so in the first of all, it is like this, that if you basically know from an electrical field is induced by electrical charges. Electrical charges commit an electrical field, so this you know, and a magnetic field, as you might know, does not have sources like or these charges, which are basically sources of these fields, but it is still that there are materials like magnets which induce this magnetic field, or an electric field itself by changing in time, which it induces such a magnetic field. So they are induced by, in some way, through charges. Even if you look into ferromagnetism or of a magnet, then you see also there are charges involved in some sense. So electrical charges, or basically the atoms, that electrons in the atoms are basically, for a ferromagnet, are responsible in some sense with their spins for it being a magnet. So, but I won't dive deeper into it. But still, you see that there is something producing these fields, but you also see that they can induce each other. And so instead of using charges, if you solve these equations in one way, you can find a way in which these fields induce each other repeatedly. So basically, you say the electric field is changing by time, and this induces a magnetic field in such a way that this is also changing by time, and again induces an electric field. And this is a wave, basically, that is produced by this behavior, a wave equation that you can get from these Maxwell equations. And without charges, then you have an electromagnetic wave that is propagating through space. And this could be concluded from Maxwell's equations, and it pretty much became clear that one aspect of one of these electromagnetic waves is the wave of the light wave, that they are electromagnetic waves, and in a certain spectrum, and this could be described by electromagnetism by then. Before, this was not clear. It was not clear that light was produced by electromagnetism. It was considered to be a separate thing, but when one realized that, one could describe light also by this theory of electromagnetism, which of course made the physics a lot easier, because now you can describe one thing by an already existing theory. So you don't need two theories to describe it, because you now have one thing. So what I want to get on with this is just to describe how in the theory of electromagnetism, this property of electromagnetic waves was discovered, or could be discovered from the theory, and then one realized that we already know this to some degree, but also a lot of other electromagnetic waves were discovered later, be it in the infrared region like radio waves, microwaves, and so on, or in the ultraviolet region like UV light or X-rays or gamma rays and so on. This was all discovered later on, but still there you had this relation to something you already did know. For gravity, this is a little bit different. First of all, from Newtonian gravity, you do not really have this case that you have basically you do not have it in such a way that you would expect gravitational waves or something like this, because this is not part of Newton's equations. This is not in there. This does not follow out of the equations. But since we now know that Newtonian gravity is not the complete theory of gravity, or cannot be the complete theory of gravity, because it cannot describe several findings that we found. For example, the rotation of the perihelion of Mercury. therefore Einstein found out that there needs to be another theory that describes gravity, and he found this theory, and this is general relativity. And this he found in 1915, so it's more than 100 years ago that he found this theory. And in this theory, if you use the equations and solve the equations, you already can predict that there has to be something like gravitational waves. And it took really a long time to experimentally confirm those. Actually, it took more than 100 years after this theory was postulated, or rather almost exactly 100 years until this theory could be, or this part of the theory could be experimentally confirmed. Of course, other parts of the theory of general relativity were already confirmed before, but this part took a little bit more than 100 years. So in 2016, the LIGO experiment, which was trying to find those gravitational waves, was in a press release showed that they had found these gravitational waves. And how they did this is pretty ingenious. So what basically happens is what gravitational waves basically are is, so if you look into general relativity, and we had it in some episodes before also where we were talking about, for example, string theory and so on, and were talking about what general relativity states, what it states about gravity, and it basically states about gravity that it is the curvature of space-time which leads to gravitational effects. So space being curved basically means that gravitation can occur. Yes. So you can illustrate this like a sheet of a blanket, and you have it stretched out, and then you pull something like a ball or something in the center, and a small marble you let go around, and then it will circle around this ball like the planet circling around the sun. So this is how you can illustrate this general relativity view of gravity. And this means that a gravitational wave is basically a ripple in the space-time. So some curvature of space-time that ripples through space-time. And this basically means that the distances between places when this gravitational wave passes through this place will change slightly. And this changes really, really slightly. You will not experience it, so it won't be like all of a sudden the car in front of you will be not 1 meter distant from you, but 5 centimeters. That's not what happens. That's not the scale upon which this is happening, because otherwise we would have come up with such a theory much earlier, because we would have experienced it in our everyday life and would have known Newtonian gravity does not describe that, so it cannot be the complete picture. But they are really, really small changes, and therefore the experiments who try to confirm this, that these gravitational waves are really existent, they have to be really, really sensitive to small changes in distance. And the LIGO experiments tried to do this, and they had 2 detectors in different places in the US. And there they had the so-called Michelson-Morley experiment built up. So it's a experimental setup that was already used in Einstein's times, and basically already then showed that there cannot be something like an ether, which they thought before would describe or would be the medium through which light can propagate. And the fact that this could not be confirmed, and that this Michelson-Morley experiment could not confirm the existence of such an ether, led to the development of special relativity, and which basically showed that light does not need a medium to go through space, and therefore special relativity was necessary in order to put relativity into the right order. But this is something for a different episode for some time maybe. But what this basically does, this experiment in this setup as they used it in LIGO, is it creates an interference pattern or a destructive interference if the distances that they are measuring remain the same. So I'm not sure if I have talked about interference yet on this podcast, but interference basically is a property that occurs with waves if they interact with each other or if they interfere with each other, so to speak. And there it is the case that they can interfere constructively, then the amplitude will increase, they will add on one another, and or destructively, and then they will cancel each other out. And the Michels-Morley experiment did it such that these light waves would cancel each other out, so they would interfere destructively, unless there would be some minor changes in the distances between the mirrors where they were passing the light back and forth. And if these minor changes were there, then there would be an interference pattern visible. So by this experiment, they could resolve really small changes in distances between these mirrors who were, I think, 2 kilometers or something apart. And with this, they could measure the effects of a gravitational wave, which were coming from the merger of two black holes. Because another thing which complicates the search for gravitational waves is that they just do not occur simply out of nothing. So for electromagnetic waves, it's pretty common that they are produced, that therefore we see a lot of light, which is good, of course. But they can be also technically produced, as you of course know. Also in a radio, they are produced for radio waves for telecommunication basically. And what you basically just need is a so-called Hertzian dipole. So with a dipole you can create these electromagnetic waves. And this is basically an antenna. It's basically such a dipole. But for gravitational waves, it's not a dipole that is needed, but a quadrupole. And this makes it a lot harder for them to be produced, and therefore usually only in really highly massive processes like the merger of a black hole or similar things, gravitational waves are produced. And then there's also the fact that they really have small effects on space-time, or are really small in the distances that we hardly can even feel it, or that we cannot feel it, but we hardly even can resolve it. And we really need highly sophisticated experiments like this LIGO experiments to show that they are there. And this experiment is really such sensitive that these distances that the LIGO experiments can resolve are of the order to 10 to the minus 22 meters. And just to illustrate how small this is about a thousandth of the radius of a proton. So it's really, really, really small. And this can be resolved by this. And with this, they could, in 2016, confirm that there are really gravitational waves in our universe. And since then, this is a really promising area of research, because if you know about light, about also the light in the universe, basically astronomy only works with the light that the universe emits. So if you are an astronomer, you look into the sky by using telescopes and similar apparatus, which basically bundle the light that's coming from the sky and make it visible to you, make it more resolved to you, that you can really see what's happening there. Therefore, light is a huge part in resolving what's going on in the universe. But this has also some problems, because as we know now, it's not only light that's coming from there, or there are parts of our universe that do not interact with light, that are not emitting any light. And this is, for example, dark matter, which is just not, as it seems, contributing to the electromagnetic force, and therefore is like invisible to us. And therefore, it is really helpful if there are other ways to look into the sky, other ways to look what's happening in our universe, in the sky, basically, and to get a deeper understanding of our universe. And therefore gravitational waves are really promising in this endeavor, and therefore it's a great area of research right now. And they are deeper looking into this. For example, there's another experiment, and this is called a nanograph, and they have a different approach for resolving gravitational waves. And what they are doing is that they have they basically say, instead of putting our detectors here on Earth, we use basically existing detectors in the universe. So what does this mean? So there are these kind of celestial objects called pulsars, and they are basically rotating neutron stars. And a neutron star is basically a star that has burned out, it's not doing any nuclear fusion anymore, because just there's basically no fuel anymore in it, you can say. And then there's a supernova happening, and as you might know, is then in some cases for really heavy stars, this would result in a black hole in the end, because then the gravitation is the only thing that is there, because due to not doing any nuclear fusion anymore, there's no pressure going against this powerful gravitational forces that are occurring there, and then it will collapse into a black hole. But if the star is not as heavy, if it's a lot less heavy, like our sun would be, then it would become something like a white dwarf, how we call it, or if it is a little bit heavier than that, but still not heavy enough to become a black hole, it will become such a neutron star. And if this neutron star rotates, then it will emit radio waves, basically. And when they arrive at us, they look like this star is pulsating, like it has a pulse, and therefore they are called pulsars. And this is pretty interesting, because they behave like a cosmic clock. They are basically, since they are pulsating, it's like a clock. They are basically a cosmic clock. And with these pulsars, this nanograph experiment can therefore build something they call a pulsar timing array, which is basically a huge many clocks in different places in our galaxy. And with this, they can basically see where there are changes in this pulsating. So if the pulses of these pulsars should be, of course, constant, they should not change. But if there are minor changes, then this can mean that there are gravitational waves behind this, because gravitational waves, of course, are ripples in the space-time. Therefore, also this would yield such changes in these pulses that are arriving us, that are coming towards us from these pulsars. And especially those changes would be correlated. So they to know that this is not just some kind of background or some other effect, you use this whole array, or this whole bunch of many pulsars. And since if a gravitational wave passes through, this will not only occur in one pulsar but the other, and they will be correlated. So you will see a correlation or a relationship between them. You can connect them to each other. They are not like randomly occurring. Then you can realize that this has in fact been a gravitational wave. And what this allows, in contrast to the LIGO experiment or to the LIGO experiment, is that it allows to really resolve gravitational waves at much lower frequencies, which would not be possible with an experiment like LIGO. And therefore they could resolve also many many low-frequency gravitational waves, and for example, they could also confirm that there are many gravitational waves being produced in such black hole mergers, where before one was thinking, one wasn't unsure how many of these black hole mergers are actually occurring in our universe, but with their measurements, it could be confirmed there are a lot of them happening. And also what they were showing, what was pretty fascinating, is so for this we need to have some background. I was talking before about that up to now, astronomy was basically done by capturing the light that is coming from the stars and the celestial objects. But and this is not only the light that is coming directly from the celestial objects, because there was a discovery I think it was in the 50s or in the 60s, where two amateur physicists or amateur astronomists were basically looking into the sky, and they were measuring some electromagnetic waves, and they were thinking this is just some error in their telescope or something that's wrong. There's some bugs on there, and they were realizing that this is not the case, and that this is actually something that they have discovered there, and this is the so-called microwave background, or cosmic microwave background, often abbreviated CMB. And what this is it is believed that this is the remnant of the Big Bang. So during the Big Bang, there was, of course, a lot of radiation emitted by all the processes that were happening there, that were going on there. And the radiation of this is still present in our universe, and this is due to the Doppler shift and different processes. This has actually, just due to the Doppler shift, this has shifted to microwaves, and these microwaves we can measure, and with this we can also resolve not only what's currently happening in our universe, but what was happening in the past. So we can resolve how the Big Bang might have looked like. We can make assumptions about that. We can build models and theories about how this could have looked like, and also confirm our existing theories with this. And what Nanograph found is that there's something similar for gravitational waves, that there is a gravitational wave background, basically, and there are a lot of gravitational waves, because gravitational waves would be also during the Big Bang. It is theorized that there would also be gravitational waves be produced in the processes there, and therefore these gravitational waves, it is believed that they are still present, and that, like the microwave background, they are in this gravitational wave background, and by measuring those we can also make more measurements about what was happening when the structures were formed, what was happening during the Big Bang, and so on. And so there's a lot of promising facts that show that there are really promising results that can be achieved by looking deeper into gravitational waves, by resolving them more accurately, and get more insights into how these are shaped, and how how many of them are present at which frequencies, at which properties do they have, and therefore this is a pretty exciting area of cosmology and of physics. And therefore this experiment, or these results that they were presented last year, 2023, and many say that this was one of the most exciting, or the most promising, or one of the greatest results that came out of physics in this year. So I think this can also be interpreted in the spirit, and I think this can also shown to be mean. So those are waves that are present in our universe, like the microwave background, but also this gravitational wave background. And I think the Bible tells us that God holds the world together by His word, and I think it's these waves being everywhere in this universe, spreading through the universe, are a symbol or a sign for His word that is passing also through this world, and holding it together, holding it in place, and holding everything together. And also it shows, if you imagine, so if you think of it that while this light, this electromagnetic life is basically, we could see it if we could see microwaves, but we can easily detect them, and this is basically easily to see, like the astronomers who look in the sky and see all this light that is going on there. But there is still some layer behind it. There are these gravitational waves which we could not see, which we cannot actually resolve with simple measures. I mean, we can resolve it by now by the highly sophisticated techniques we have, but it's a lot more hidden. And I think this is also a sign that something that sometimes the things of God are more hidden. They are not really directly accessible to us, and that we have to put some effort in to find them. Not effort in a sense of works of the flesh. That's of course not what I'm talking about, but I think the Bible always talks also about an endeavor that we take to uncover his mysteries, that it's not just that he lays it all out before us, but we need to uncover it. We need to have a passion and a urge or a hunger for more of him, to really experience him, to see more. And then, as with the gravitational waves, where we can find out a lot more about the universe that we did not know before, as it is in this case, we can, with God, if we really dig deeper and go deeper into what his word says and what he reveals to us, we can understand a lot more. We can get to know him a lot deeper and understand a lot more things, but we need to be willing to dig deeper, to allow his mysteries to be unveiled in front of our eyes. And I think this is really what he's calling us for, to come closer to him and to dig deeper into his mysteries, that he can show us what he's thinking about us, how he sees us, and what he has planned for us. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there is always at the beginning of a month or of a block, there is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast, and then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is My latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that, and now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.